It gives me great pleasure today to welcome you to the Warren Lecture today. I'm pleased to introduce my colleague, our newest member, who is Pedram Mortazavi. He joined us in January of this year. He got his PhD from the University of Toronto, and his expertise is in large-scale structural testing, numerical modeling, advanced simulation, and also expertise in steel structures. So without further ado, I'd like to welcome my colleague, Pedram Mortazavi.
Thank you. Thank you so much, Kathy, for the great introduction. It's such a pleasure and a privilege to present the Warren Lecture this week. So I'd like to thank the department, Paige, for the great suggestion, and Judy, Molly, Mary, and Shar for organizing and facilitating. So the topic that I'm going to be talking about today was done during my PhD as the main topic of my PhD. So first and foremost, I would like to acknowledge my PhD advisors, Professors Konstantin Christopoulos and Professor Osan Kwan. I would also like to thank and acknowledge CAS Connects, specifically Dr. Mike Gray and Mr. Justin Binder. Pretty much everything that I'm going to be talking about, they were involved one way or another. So really, I'm presenting on behalf of a big group of engineers. So I'm going to start my presentation by talking a little bit about the concept of resilience. Many of us are familiar with it, of course. Then moving on to the backgrounds of the project, some background information, and then moving on to cast steel replaceable modular yielding links, the system that we're proposing in this project, and going to the experimental program and validation of them, hybrid simulations, which we did, and then some design improvements, including the mitigation of residual deformations, and in the end with some summary and conclusions. So resilience is a topic that many of us are familiar with, but I'm going to define it because it will come up. So the idea is that, well, the definition goes as follows: the ability of a system to recover to its original condition quickly after a shock. And that could be for a community, could be for one building or neighborhood, a system, any system really. So the idea is that you have 100% functionality. A shock is introduced into the system. There's a drop in functionality. And the question is how fast and how quickly you can recover back to full functionality to resume business. So the state of practice currently in earthquake engineering is that we don't think too much about resilience. We allow damage in the building to provide life safety. So this is damage to a parking garage after the Christchurch earthquake. It's an EBF. So what we have is the yielding link in the middle. We're going to talk about EBFs a lot. But essentially, the yielding link did its job. The structure didn't collapse, but the yielding link yielded. It developed a lot of residual deformations, as you can see here, and it even fractured in some cases, right? But the building stood. But if you're the owner of that parking garage, the next day after the earthquake, you come in, you see this. And the question is, can you resume business? Or what should you do? Should you hire engineers to look at this? Do you demolish, or do you repair, or demolish, redesign, and rebuild? And that's not an easy situation, given that the earthquake or the natural hazard happens to all the buildings at the same time. So it's not like one car getting into an accident in the city. It's like all the cars get into an accident, and all of them will seek mechanics to fix their cars, right? So it's a very difficult situation. And that's not something that would just happen to EBFs. This is, for example, dog bone or reduced beam section steel moment resisting frames. And this is actually an experiment, but imagine being in a building, and then after the earthquake, the building doesn't collapse, but you come in and you see this at all the corners. And the question is, how soon and how much money does it take, and how much time does it take to go back to functionality? To put things in context a little bit better, I'm going to talk about the Christchurch earthquakes. That is a very famous case study on the topic of resilience. So Christchurch was hit by a series of earthquakes in 2010 and 2011, and these guys are experts in earthquake engineering. So after the earthquake, only 2 buildings collapsed, right? But a lot of damage. So moving a year after the earthquake, this is the central business district compared to what it was after the earthquake. And these buildings didn't collapse during the earthquake. Again, only 2 buildings collapsed. But the extent of damage was so significant that they had to tear down and rebuild them. And again, everyone is seeking consultants, demolition, builders, and so on to get those services. And Christchurch, after 15 years now almost, or 14 years, still hasn't fully recovered. So it gives you some idea in terms of the socioeconomic impact of a natural hazard if you don't think about resilience. And like I said, right now in the field of earthquake engineering or natural hazards, we aim for life safety. And it's because that was the need at the time, especially after the Northridge and Kobe earthquake in Japan. The immediate need was to assure life safety. But now with these new experiences, which was really a reality check to the structural engineers and the earthquake engineering community, the message is clear. We have to move away from conventional construction only and move towards more resilient systems. So as an example of this, I should also mention that these are actually the same part. It may not look like it, but you can see by this reference and this green belt. So essentially, if you go stand on that side and look at it from that view, you see this, right? So again, as an example of this approach, I'm going to talk about the work that I did in my PhD, which was on the resilient design of EBFs with cast steel yielding links. So a brief background on EBFs. They're not a new system. They have been around since the 1970s. The idea is that you have a portion of the floor beam between the 2 braces that would eccentrically braced frame. Yes, so that portion, yeah, I should have said that. The portion of the beam between the 2 braces, so the braces are eccentric. They're not concentric. They don't line up. So that portion of the beam between the braces is supposed to dissipate the energy. We refer to it as the yielding link. So that's the fuse in the system. And because the braces are eccentric, they allow for more architectural opening. So the architects like them. They were first introduced in Japan by a researcher called Fujimoto. And then legend has it that Professor Igor Popov from Berkeley one afternoon sat down with Takanashi, another Japanese engineer, and they worked out the mechanics of the system, which resulted in a report with Charles Roeder. And then Professor Popov started getting students on the topic, published a lot. The first database of tests on EBFs contributed to the adoption of the system in the 1988 Uniform Building Code. And after that, when A992 steel became common in steel construction, Okazaki and Engelhardt did additional study on links on that. So when we talk about EBFs, there are a number of configurations. In all of them, there's, you have more architectural opening, and you have that yielding link, which I'm showing here with red. And in this presentation, I'm going to focus on the most common type of EBF or the most common configuration. But pretty much everything that I'll talk about applies to the other configurations as well. In terms of EBF classifications, depending on the length of the yielding link, you may get a shear critical link, meaning it fails in shear or yields in shear, or a flexural critical link, meaning it fails or yields in flexure. So essentially, if it's shorter than a certain threshold, it would yield in shear. If it's longer than a certain threshold, it would yield in flexure. So looking at them more closely, I have the free body diagram, plasticity, different response parameters. What I want you guys to look at is the plasticity. In shear critical links, you get a uniform plasticity on the web. It fails basically or yields in shear, so you get a uniform shear strain. In Flexural links, on the other hand, you get localized yielding, right? So you get flexural curvature concentrated at the end. So it's not as, I guess, efficient use of the material as shear critical links. And that's recognized by the, codes where they allow more rotation, more plastic rotation for shear critical links. They allow you to design them to go to 0.08 radians, whereas flexural links can only go to 0.02. Going to advantages and disadvantages of EBFs. So the main advantages are that they're more stiff compared to MRFs, moment resisting frames, so they control the drifts better. And they're not as stiff as SCBFs. So the design of the capacity protected elements is not as much of a challenge, especially the foundation. So they provide a nice, almost the best of both worlds, right? And however, there are some challenges. So the first challenge is that now in your design, you have another design parameter to control. So other than the force controlled elements that you designed to provide the capacity, and other than controlling the drift, now you have to control the rotation of the link as well. It's just another check. And it's interesting, just one additional, I guess, check makes the design much more iterative. The other problem is that most steel sections are designed to work well in flexure, like W sections, right? We move the flanges to maximize the moment of inertia. But here, we prefer a shear mechanism. So what do? We add stiffeners with welds to make sure we get a stable shear yielding mechanism without web buckling. So that makes the detailing challenging. And the design process is iterative, I mentioned, because we have another parameter, but also it's challenging because the yielding link is integral with the floor beam. If you recall the parking garage in New Zealand, it's one element, right? So it's really hard to prevent yielding outside of the link. We typically want to capacity protect the elements outside of the fuse, right? And same thing, really, obtaining an optimized solution for link rotation and drift is not easy. And lastly, again, because it's integral with the floor beam, the repair process is very challenging. So about 15 years ago, a former colleague of mine, Dr. Nabil Mansour, working with my PhD advisor, and Robert Tremblay as well, they proposed fabricated replaceable links. So essentially, you have a W section that is connected to two end plates, and then they are bolted to your floor beam. And that was a great step forward because it decouples the yielding link from the floor beam. So that was useful. However, there are a number of challenges here. So first of all, the weld between the flanges and the end plate have to be complete joint penetration welds. So that's expensive. And also, you have to get rid of the weld access holes. Otherwise, you get a premature failure like this as opposed to that. And lastly, because this is an energy dissipative element, those would be considered demand critical welds. And they may require non-destructive testing, which would drive up your cost, right? So despite those challenges, actually going back to the Christchurch earthquake, in the rebuilding efforts of Christchurch, these replaceable links were actually adopted. So they were well received by the engineering community. And it's interesting, architects like them. They put nice colors on them now, especially after the earthquake that happened. Just because it looks nice, but also it's a marketing strategy as well. They tell the investors and the occupants that, look, this building is protected. Of course, they don't understand the mechanics of the system, but just seeing it helps, right? So if I go back to that matrix of advantages and disadvantages with what Nabil, my good friend, worked on, he solved a couple of the problems. So challenging repair process, right? Because you can just replace it after the earthquake, or challenging to prevent yielding in the beam. That was solved too. Some of them remained, and actually detailing, I would argue, got worse, more effort, because you have to now, all the things that I talked about, get rid of the weld access hole, complete joint penetration welds, and so on and so forth. So steel casting, we've had a lot of, I guess, success stories at the University of Toronto in my PhD advisors research group, and also with CastConnex, the industry partner of the project. So steel casting is another way of really fabricating steel. And what it does is that you basically use a mold in a sense, right? And it gives you freedom of geometry. So these are two famous graphs that show as the shape complexity or mass production increases, steel casting becomes a better option in terms of for economical reasons compared to the welded fabrication, right? And also, it's been maybe 2 decades or maybe a decade and a half that people have started using steel casting for ductile elements or structural fuses. That has not been the case before. So given the success stories that steel casting has had, it was very natural for us to eventually go towards a steel casting element as the fuse in EBFs. And that brings me to the system that we've worked on in this project. So cast steel replaceable modular yielding links. I actually have a small replica of it that maybe we can pass around if you're interested to have a look. Oh, sorry. And what it is that it's a yielding hysteretic damper. And much like replaceable links that we saw, it has 2 end plates that connect to the floor beam with bolted connections. But at the ends, you have 2 yielding regions that are basically 2 hollow box tapered sections. And they're tapered such that their capacity at every point matches the demands from the moment diagram. So remember, the moment diagram in yielding links was a linear moment diagram in double curvature, right? So if you size it appropriately, you get simultaneous yielding everywhere. But this time around, it's a flexural yielding. It's not shear yielding. So you don't need to provide stiffeners. The other thing, again, they're replaceable, so you can easily repair your structure. And also, they promote modular construction. So everything below the column splice can be fabricated in the shop and shipped to the site, and then the top piece as well. And then they get assembled by the link in the middle. So also a lot of time and effort during construction will be saved. So in the first design iteration, we had 9 sizes. I'm showing them with EBF followed by a number. That number is the nominal shear capacity of the link in kips. The same number is shown in the brackets in kilonewtons. So that means the shear load at which the entire yielding region has yielded. This is what they look like in our structures lab. My co-advisor, Professor Osan Kwan, and our friends from CastConnex. And designing them is not that hard once you know what to do. So essentially, you want to know what VP you're aiming for, and you want to know the length, right? Once you know that, you can size each section such that the plastic moment of that section, or ZFY, times 2 divided by the effective length, or the length between the 2 sections, is VP. So I have VP and I have EF. I can play with the section, and FY is known, sorry. So I can play with the section to get the section that works. And we also control a number of other things. For example, B over T, we put a very strict, B is the length of the flange. We put a very strict limit of 6 to make sure it doesn't buckle locally. And the moment of inertia about the X and Y axis, we limit it to 1.5, not exceeding that, to make sure lateral torsional buckling is not a problem. That's from a study by Michel Bruneau. And we maintain constant area. So as this tapers, it gets thicker, right? To maintain the same area such that under combined effects of axial load and moment, it would also give us simultaneous yielding. So if we go back to that matrix of EBF limitations or challenges that I mentioned earlier, with our proposed system, we believe all of those will be solved. And we're going to see how in this presentation. So you propose a system, you have to test it. So moving on to the experimental program. In the experimental program, we had two test setups. One was the component test setup, and the other one was the system level test setup. I'm going to talk about each of them. So the component test setup was built on a universal MTS testing device with a force capacity of 2,700 kilonewtons and a displacement capacity or stroke of plus minus 6 inches, 150 millimeters. And closer look at it, these steel elements were fabricated and PT'd to one another and connected to the top piece with a clevis and attached to the specimen, another close look, by bolts. And the setup was designed such that when it would move up and down, it would induce the same loading condition on our yielding link that it would see in a real EBF. And with these setups, obviously, you do, first mechanics, you design it, and then you go to finite element analysis, and you make sure that everything in the design is sound. You can tweak it and refine it at that point as well. Excuse me. And here, we've PT'd all of these together. We wanted to see the gap opening, so that gave us some good idea, and also the performance of the link in the setup. The system level experimental setup was a one-story EBF. And in one of the tests, we actually also put the concrete slab on top just to see the interaction. So the steel EBF was PT'd to the strong floor and loaded by means of two 1,000 kilonewton or 220 kips actuators. So 2,000 kilonewton from one side. I guess the main thing that I would like you guys to remember from this setup is that if I have a one-story EBF and I load it with two forces, if the two forces are equal, I get no axial load in the link. But if I only have force on one side, so F1 is non-zero and F2 is 0, which is the case for my setup, we get axial load in the link. So that's what I want you guys to remember, as it will come up. Moving on to the test matrix. So I said we had 9 link sizes. In the component setup, we decided to do 6 tests. 2 of the biggest ones, 2 of the smaller ones, and we did 2 to assess repeatability. And we did 2 medium-sized links, EBF 100 and EBF 77. In the frame setup, we decided to do 3. 1 EBF 77 without slab, and 2 EBF 100s, 1 with the slab, 1 without the slab, to assess the effect of the concrete slab. In all of the tests, we subjected the system, or the specimen really, to the AISC loading protocol for qualification of yielding links. Going to one sample test, my component test on an EBF 77. So you see the hysteretic response of the link on the top left. And as you can see, very good stable hysteretic response. Close-up view of the link at the left middle and left bottom. I should mention here that conventional links are designed to reach a plastic rotation of 0.08 radians. So in terms of total rotation, maybe 0.09. But we were able to reach 0.2. And then after that, we fractured. You can see the crack opening here. So almost 2.5 times of what the code requires. So both us and the industry partner were really happy. Some additional results on the EBF 35. Again, great performance. We actually reached 0.19 and did 2.5 cycles, so way more capacity. EBF 77 is what we just saw. EBF 100 also excellent performance. When we went to the largest link size, they actually demonstrate or showed a more moderate capacity of 0.11 radians. So I'm going to come back to that. But before we talk about why and what we did to address that, let's look at one of the system level tests. So this is an EBF 100 without the slab tested in our one-story frame. And you have the close-up view of the link, hysteretic response. Again, remember, when the actuators are pushing, the link is in compression, shown on that side of the hysteretic curve. When the actuators are pulling, the link is in tension, shown on this side of the hysteretic curve. That's why you get that skewed response. So when you're putting the link in tension, you're punishing it more So it shows more hardening. So here we were able to reach 0.15 radians with the link in tension, went all the way to the other cycle. When we reached for 0.17, we opened the crack, but we closed the crack, redeveloped the strength, went all the way to the other side, and then we stopped the test because the crack was starting to look very scary. So what were some of the findings from our experimental program? So one, the link overstrength. So for all of the links that I tested, and these are the aspects that we used in the codification. I'm going to talk about that briefly, but towards the end. But essentially, if I map the ratio of the link shear to the nominal capacity at every rotation, I get the overstrength, right? And then depending on the rotation or design rotation that I'm aiming for, I know what is the overstrength for the design of the capacity protected elements, right? Also, because we tested in the frame setup with axial load, that gave us the opportunity to study the effect of axial load on the link. And you can see for tension cycles and compression cycles, as you increase the rotation, the drop in compression goes down and increase in tension goes up. So it looks something like this. If I show the EBF 100 tested in the frame versus a component test, you see something like that, right? It's a second order effect. That's why as the rotation goes up, this effect increases. It's almost like a small P delta effect for those of you that are familiar with that. We were also able to, like I said, study the performance of the slab and identify damage indexes. So these are useful if you're talking to your client in terms of performance-based design, what they want to achieve in their building, what they want to see in their building the day after the earthquake. In terms of the slab effect on the response, we saw that the overall strength, especially at larger cycles, didn't change. So if I map the shear, overall shear in the test with the slab for EBF 100 to the test with EBF 100 without the slab, I see that at very small rotations, the slab is contributing to the strength, which makes sense. The slab hasn't cracked as much. And as you move, it rapidly loses its strength. So in terms of overstrength, the slab is not doing much. But we saw that the unloading and loading stiffness with the slab is actually much stiffer, right? And there was a reason for that. When we examined the videos, we saw that, well, this is the initial position. You get some cracks, but at every cycle, your cracked piece basically articulates and develops these compression struts that would lock up. And when you're reversing the load, it adds to the stiffness. But as soon as the link yields, it relaxes. Because when it yields, it also gets longer, right? When it's getting longer, it relaxes. And then through that mechanism, at the end, you have all of these corners chipped off. And you can see it actually towards the end of our test. We also got a chance to apply digital image correlation and to study our specimens using that. So for those of you that are not familiar with it, what you do is that you apply a pattern on the area of interest. And for me, that was the yielding region for obvious reasons. And you put a camera. And that camera takes a picture of this region at the beginning of the test. So it knows the location of each of those, particles with respect to one another. And as the system deforms, it can track how much each point or points have moved with respect to one another. So again, we studied that region. This is the strain field that we got from DIC. Looks pretty constant along the yielding region, so it worked as we intended. But I also verified that with my abacus model, setting them to the same limits and the same numbers. You can see we got a pretty good match. So it was also a good way to verify our model. Okay, so now going back to our experimental results. I said that the small and medium-sized links worked very well, achieving very large rotations, but the big one only reached 0.11. So we sat down and we looked at why the reason is, and without getting into the mechanics of the link, we realized that the shear capacity of the link has an indirect correlation with maximum ductility. So the stronger the link, the sooner it would fail. And that's what we saw in the experiments as well. But the length of the link has a direct correlation with ductility capacity. So if I make the link longer, I can achieve more rotation. So in the next stage, we introduced finite element analysis and fracture modeling actually in the design process. So we would start with the length, and then we would assess the fracture capacity, and then we would increase that length if it wasn't enough to get more fracture capacity. So in the second design iteration, our links looked like this. The strongest one was also longer to achieve more or less the same rotation, and the smaller ones were shorter. So going back to a new, I guess, product line or the new design of links, we had something like this. So the rotation was much more uniform. So then we almost repeated the experimental program. This time around, we only tested 4 of them, so 2 of EBF 45 and 59. We tested them again in the component setup and in the frame setup. I'm only going to talk about the component test in the interest of time. And you can see, because these are shorter now, I had to use these very thick shim plates so that my setup would accommodate them, right? What I'm showing here is the hysteretic response, and I'm showing the target ductility that we aimed for in the design. So you can see our link was able to reach that for half a cycle, and then afterwards it failed. This one, I guess because of imperfections, in the first cycle of failure, it failed here, but then upon closing, it was able to reach the target ductility. So we were pretty happy with our design methodology and the performance. So even though we tested only 2, the capacity matched the target. So we believe the rest of them should also match that, because the same methodology was used for all of them. In these tests, I also did DIC, but this time around, I used the commercial program, GOM Correlate Pro. It also gives you a strain field, similar, I guess, observation, uniform, plasticity, comparison with Abacus very well. But it also gives you a nice video. So this is the yielding portion of my link. So you can see I'm showing the strain in the X direction. So you get all of these nice strain fields, and you see how they progress as the link deforms. And these lines that you see close to 0 strain, those are just the imperfections on the surface. So we validated a system. We saw some limitations. We improved it. What's the next step? We only saw the response on the reverse cyclic test. I was just talking in another seminar, and we talked a lot about this. It has been shown that hybrid simulation can also be very useful in assessing the global response of the system, and also understanding the limitations that it might have. Do we know what hybrid simulation is? Show of hands if you're familiar with it. Okay, so I'll just quickly explain it. So in hybrid simulation, we take a critical portion of the structure, we test it in the lab, and then the rest of the structure is modeled numerically in a numerical model, and we establish communication between the two. So then let's say I have a whole building. The first floor yielding link is only tested in the lab. The rest of the building is in the computer. So I subject my numerical model to an earthquake, and now my global model is talking to the specimen. At every step of the earthquake, it communicates the displacement demands to the lab. The specimen experiences those. The force and displacement are fed back to the numerical model. So it's almost as if your stiffness matrix is talking to the specimen, and it's getting updated. So long story short, we decided to do hybrid simulation on an EBF structure. So we designed a 4-story EBF in downtown Los Angeles. I'm showing a rendering here. We have 8 EBFs in the building. In the plan, they're shown here. Due to symmetry, if we remove accidental torsion, we can argue that studying only one of them would suffice. So that's what we did. This is my overall numerical model, if you will. And everything was modeled numerically in OpenSeas, except for the first floor link, which was tested in my component test setup. And why I did that, because in my component test setup, I didn't have any axial loads. And in the link here, I didn't have any axial loads. So it was a reasonable, I guess, correlation there. For the links that were modeled numerically in the hybrid simulation, we developed the numerical model without getting too much into it. We had a series of, we discretized the link, yielding region into a series of elements with fiber section. And each section basically was modeled based on the specs that we get to the foundry, right? So, and we also modeled the shear elastic stiffness and aggregated it in OpenSeas. So going to the first hybrid simulation that we did. So this is the 4-story building. The first floor link is here, tested in the component setup, and that's the hysteretic response. This was the L'Aquila, Italy earthquake. It's a pulse type earthquake. For those of you that are familiar or may not be familiar, pulse type earthquakes push the building to one side with one big pulse, and then after that, it may not recover as much. So you're left with what we call residual deformations. And you can see this is the rotation in the link. So this is almost oscillating towards the end of the earthquake. And you see you have 0.07 almost residual rotation. So talking about replacing it and restoring it back to functionality, that is the building, that will be a huge challenge, right? So in retrospect, we should have known that, but this is the great thing about hybrid simulation. It reminds you of things that you may not immediately know or think about, right? Because in these, the loading protocol correlates to the earthquake. Nevertheless, that gave us a great opportunity to also calibrate our numerical model to real random loading histories, so made our numerical model more robust. We also, after doing 3 MC earthquakes on one specimen, so subjecting it to a lot of deformation demand. And I should add, after each earthquake, we would recenter the specimen. So, the red is the response to the earthquake. The black line is the recentering. So you have to come back to 0, right? So that also adds additional strain or, plasticity or demand to the link. After that, we wanted to assess the remaining ultra-low cycle fatigue life. And we saw that it only reduced by 1 cycle after 3 MC level earthquakes. So comparing the response of the EBF 100 without any earthquakes that you saw earlier to the response of an EBF 100 that had seen 3 earthquakes, you would see only a reduction of 1 cycle. I also did another hybrid simulation on a 2-story structure. I'm not going to get into the details of the design of this. I'm just going to say that this building was designed such that the top floor link here would experience the same level of axial load that I had in my frame setup. And I did that, admittedly, I tweaked the design to get that same load. And I wanted to see what that axial load would produce or what effect it would have on the dynamic response of the building. But we modeled 2 of these EBFs in the plan in our numerical model. Everything was modeled numerically except for the top floor link that was tested in my frame setup that would induce the same axial load on it. The first floor links, I should add, didn't have any axial loads, only shear demands and moment. So looking at the hybrid simulation here, so this is the top floor link, and this is its hysteretic response. So it's being tested in the frame setup. So that's the one you want to be looking at. So on one side, you can see it's developing the tensions, lots of overstrain, and on the other side, it plateaus because it's in compression. So it was interesting to study the system under the effect of axial load under real earthquakes, but the same trend that we're seeing is lots of residual deformations. This time around, it's close to 0.1 radians. And in terms of replacing the link and restoring the building back to functionality, that would introduce significant demands. Nevertheless, again, good opportunity to further calibrate our model to also ensure that it works well for combined effect of axial load and moment. Good agreement here. And at this point, we said, okay, what other improvements should we make? Mitigation of residual deformation was the first thing that came to our mind, given what we saw in our hybrid simulations. So I spent a lot of time. I looked at a lot of options, some of them with strong back systems, some of them with PT rods, some of them with what we call sked braces. And eventually, we converged on probably the easiest, or not the easiest necessarily, but the most economical option. Because nowadays, there are many approaches for ensuring self-centering behavior or mitigation of residual deformations. What is the real challenge is doing that in a cost-effective way, that it could be mass implemented. That's the main challenge right now. So what we decided to do was to have HSS beams that are in parallel with the yielding link. And essentially, they would act as a strong back or a dual system. So they would give the system more post-yield stiffness. And these end connections, we detailed them in a special way with slotted holes such that they would give you bending moment resistance through a couple in these two, but release the axial movement. Because as you know, the link would get longer. And if I exaggerate it, the EBF at some point may look like that. So we don't want axial load to develop in these HSS beams. So I guess in a nutshell, this is the system. And when it deforms, the elastic element or these HSSs, this is a highly exaggerated figure, obviously. This is longer, so it doesn't yield as quickly as that, as the link. And they're basically two springs in parallel, if you can see that. And this would stay elastic because it's longer, and it would provide post-yield stiffness. Again, I did a lot of parametric studies to see what is the optimum post-yield stiffness that I need to aim for. And the number that we reached was 3 to 4% post-yield stiffness of the elastic stiffness of the link. So I know the elastic stiffness. I know what my HSS should be. So it becomes a very small element, actually. So now going back to the same hybrid simulations that we saw, I implemented that HSS system in my building. So the black line here shows the response of the original system with no recentering that we saw. The blue line is the response of the modified system. So you can see right off the bat, and this is in the component test setup, the residuals are controlled much better compared to the case with no recentering. And I'm only showing the response of the link here. The base shear goes a little bit up because the other one has 4% more post-yield stiffness, right? But I'm not showing that there. So this could very well make the difference between not being able to replace the link or requiring a lot of work versus quickly taking it off after an earthquake and putting a new one in. So obviously, as engineers, we're trained to understand these figures and numbers, but I always find a picture would also be very helpful. So these are the deformed shapes of the link after two hybrid simulations, having gone through two earthquakes, separate ones, without any recentering. So I'm going to superimpose the same link, but with recentering. So we were able to go from this to that by just adding two, HSS members. So this could easily be replaced. I don't know if this can be replaced that easily. The same thing for the two-story building. That one, if you recall, had almost 0.1 radians or 0.09 radians of residual rotation. So again, the blue line is with the recentering. The black line is without recentering. So we see the same thing. We went from 0.09 almost to maybe 0.01. And maybe 0.01, 0.02, that could be the threshold of replaceability. So the system works very well in terms of reducing and mitigating the residuals. Again, doing the same thing, this time around looking at the frame, because these tests were done in the frame. Without the recentering, we were here. With adding the recentering system, we went to this. So we went from that to that. So great improvement in terms of replacing it and restoring the building back to functionality. After that, I did a comprehensive numerical study on the response of EBFs. I modeled these in open seas under a lot of ground motions to complement the findings of the experimental program. And then we were able to propose design guidelines in the last chapter of my PhD, which I'm very happy to share that they are going to get adopted in the next release of the Canadian Steel Code, CSA S1624. Obviously, that doesn't exist yet, so I brought the 19.1. But essentially, we provided design guidelines for the design of cast steel replaceable links and also design of the EBF or EBFs that adopt the cast steel links. In the last year of my PhD, I also had the pleasure of working at CastConnex through a fellowship program. And there, working with other engineers, I had the opportunity to study the first building that was considering adopting our proposed link. So it was a very nice, circle to go through all of that, coming full circle to, from all the way to experimental validation to design provisions and implementation. So summary and to conclude, in this project, we looked at the performance of cast steel replaceable modular yielding links, and we did the first comprehensive experimental program and characterized their different response parameters. Based on the findings, we looked at a second generation of cast modular yielding links, and they were designed to target a more uniform ductility, which again, we tested in the second experimental program. We went all the way to doing hybrid simulations on EBFs designed with the proposed links to look at their global response under real earthquakes. And when we saw that we had large residual deformations, we developed a low-cost system for mitigation of residual deformations, and we also validated that through additional hybrid simulations. In the end, we synthesized all of the findings for codification of the system and implementation in real buildings. So with that, I would like to thank you for your attention, and I'd be happy to answer any questions that you might have. Yes, Sakti.
Oh, 1 second.
Thank you for your lecture, first of all. Because the EBFs were cast, was it ever considered for them to have, well, because they were already semi-hollow, was it ever considered for them to have like any form of internal structure so you can resist, I guess, certain motions that you didn't want it to?
You mean making them like solid?
Like instead of solid, like consider
Other
already
shapes.
Yeah, other shapes like
Yes.
like rib cages, for
Yeah,
example.
that's a great question. So before my PhD, my advisor had a master's student. Her name was Kyla Tan, and she actually did the first finite element study on links, and she looked at so many geometries. She looked at cast steel links with corrugated web, or cast steel links where you had rings next to each other, and each of them would yield, or ones that you would only taper the width, ones that you would only taper the height. And eventually she reached a case where she was tapering one of those, but not the thickness. But that gave us a good starting point. So when we started working on this project with CastConnex, we changed the thickness taper, and that gave us the first design of links. But my point is that if you look at the mechanics of it, in order to ensure simultaneous flexural yielding, the shape makes sense. But on top of that, there was a master student who looked at maybe 7, 8 configurations, did FE on it. She looked at stress concentration and strain concentration, overstrength, and eventually found out that the tapered solution is the best one. Hollow box tapered. Because also hollow box has a very small shape factor. Shape factor is Z, plastic section modulus, over S, elastic section modulus. The lower shape factor means overstrength is lower. And that's a desirable characteristic for energy dissipative elements, because you have to design everything around it to stay elastic or capacity protected. So the less overstrength it develops, it's a good thing.
Okay, my question is, not every structure is a parking structure where you have exposed structure. In a real building, everything's hidden. So you keep saying it's easy to replace, but I have a hard time envisioning it being easy to replace, especially since the structure of a typical building, for example, a 12-story building you showed, the structural components are only a small fraction of the cost of that building. If you're going to have to tear up all of the architectural components, you really potentially haven't saved anything. My question is, have you discussed this with architects to try and modify how buildings are designed so access to the replaceable units is enhanced?
Right. Great question. So I guess to your first point, now, thankfully, especially after the recent earthquake in Christchurch, we're moving away from hiding the structural component to actually exposing it. And that's something that you see in New Zealand, you see it in California a lot, and people actually like it. So that's one solution. The second thing, for EBFs, after the Christchurch, actually they repaired a few conventional EBFs and replaced it. So they basically opened just so you know this is your EBF. So you cut a hole in your structural slab, and it's not, it is intrusive, but not as intrusive as you had, let's say, a moment resisting frame where you had to go to both joints. You know what I'm saying? Because you know it's here, you can just cut a hole, maybe 1 meter by 1.5. And they did that for a hotel structure in Christchurch that had conventional links. So they opened it, they cut it, they took it out, they put end plates welded, and then they brought the new replaceable one and bolted it in. So it's been done. It's not as easy as the case that it's exposed, but for EBF actually, because the damage is very localized, it's easier, I would say. I didn't personally talk to architects, but I've seen that it's been done in the field, even for conventional damaged EBFs. Thanks, though. Good, great question.
There are other questions. I have a question about, you had done the experiments and then you noticed a difference between your model and the result. So you recalibrated or made modifications to your numerical model. Could you comment on what some of those adjustments that you made were? Because then you made further adjustments after your second set of
Another
data.
great question. So because our numerical model was a fiber section, it actually worked quite well. So there were very little tweaking that we had to do, maybe with post-yield stiffness a little bit. So with these stable yielding systems, you know, I've worked also on BRBs and other systems, and it's the same thing. You have a stable yielding system that with every cycle you get hardening. And sometimes when you're calibrating that in your numerical model, the modeler may not, may mistakenly use more post-yield stiffness to account for hardening. So that's one thing that is easily overlooked in a reverse cyclic test, because you just see forces going up, right? But if you do an earthquake with a pulse type motion, it's almost like a monotonic test, if you will, right? So you get that post-yield stiffness captured, and then in the reverse, you get the hardening. So that complements your, you know, calibration to experimental result, reverse cyclic experimental results really well. But also to add to that, what I found is that in the other presentation, you saw the SCBF prediction were really good, even though it's a more complex system. It has buckling, negative stiffness. On the other side, it's yielding. And the reason it worked better, because the numerical model was using a fiber section, which accounts for the physical mechanism of the structural component rather than a force deformation calibration. So when you capture the mechanics of the system in your model as much as you can, you just calibrate material and you input that. The rest is taken care of by your model, right? You only have uncertainty in the material. But in cases where you have a stick element, force deformation, it's much harder. So I guess coming back to it here, because we had fiber sections, the numerical model was more robust to begin with. But the only improvement I would say would be between post-yield stiffness and cyclic hardening.
Thank you. Any other questions? One more question.
Thank you very much. Very comprehensive study. Just to clarify, I heard the word once. I just want to make sure that it was consistent. The dynamic response of a structure or a model is totally different from a static structure. An earthquake is a dynamic load. Did your modeling and your experimentation capture the true dynamic response?
Yes, so that's also a good question. So in hybrid simulation, that's the main advantage. So I think I have to go back a lot of slides, but I'll just say it. In hybrid simulation, the good part is that you're still considering the dynamic effects by doing dynamic integration in your integration module or your numerical model. So all your accelerations, velocity, and ground motion is captured there. So if you look at the equation of motion for the dynamic response of structures, there's a KU part, the internal forces or the spring forces. That is only coming from the lab. The damping forces or the inertia forces, all of that is in the numerical model, and that's accounted for in hybrid simulation. Now, the question could be, is it 100% accurate? Obviously, if you do real-time hybrid simulation, you would capture those in the lab. So it has that advantage. But the problem with real-time hybrid simulation is that your simulation is real-time. So they're communicating. And then if you make your numerical model robust, that could delay the communication and you could have problems in your simulation. So what you would see is that in real-time hybrid simulation, the structural model is very simple. So, for example, in my models, I had, first of all, the other links were fiber sections, discretized. I had connection, gusset, everything. You wouldn't be able to do that in a real-time hybrid simulation. And one criticism that real-time hybrid simulation receives is that people say, you go through all this trouble to capture the response of a critical part of the building, in the lab, then your numerical model is very simple. So how do you justify? But that is not to say one is good or bad. You just need to know where to use the application. We knew that our elements or links were rate independent. That means whether you load them very fast or load them very slowly, they give you the same response. So pseudo-dynamic hybrid simulation for our application was a justified approach. Yeah, thank you.
And thank you very much for that outstanding presentation. We're very excited to see what's coming next and very happy that you're one of our colleagues here. Thanks,
Thank you,
Pedram.
Kathy. Thank you so much.